Okay, and our last speaker this morning is Kuiling Ding. Kuiling Ding received his BS degree from Zhengzhou University in Henan, China in 1985, and in 1990 earned his PhD in physical organic chemistry from Nanjing University under the supervision of Professor Wu. Between 1990 and 1998, he returned to Zhengzhou University as a researcher, being promoted to full research professor in 1995. Then in 1999, he moved his research laboratory to the Shanghai Institute of Organic Chemistry, where he is currently a professor of chemistry and its director. Although his academic appointments are grounded in China, Professor Ding has forged various international collaborations throughout all stages of his career. From 1993 to 94, he performed postdoctoral research with Professor Teruo Matsura at Ryukoku University in Kyoto. Then from 1997 and 1998, he was a UNESCO Research Fellow with Professor Koichi Mikami at the Tokyo Institute of Technology. And lastly, in 2003, Professor Ding was briefly a visiting professor at the Research Center of Material Science at Nagoya University. Professor Ding's research interests include the development of new chiral catalysts and methodologies that enable asymmetric organic transformations, and toward this end he has co-authored over 150 scientific publications and filed over 20 patents. Perhaps nothing attests more to his contributions in organocatalysis and cross-coupling than his internationally recognized advisory responsibilities. He currently serves on the advisory board of 3 international catalysis symposia, as well as those of 8 high-impact journals. He's also received numerous scientific awards, including the National Natural Science Award of China, the Eli Lilly Scientific Excellence Award in Chemistry, the first Yoshida Prize of the International Organic Chemistry Foundation of Japan, and in 2013 he was elected to the Chinese Academy of Sciences. Professor Ding's research interests in sustainable catalysis are in concert with the Chinese Academy of Sciences Innovation 2020 initiative, which Ding himself described in a 2013 issue of ACS Catalysis as integrated efforts which must focus on the challenging issues related to population, health, and agriculture, resources, energy, and environment. Please join me in welcoming Dr. Kuiling Ding as he presents an overview of his laboratory's recent investigations into cooperative catalysis in asymmetric synthesis.
Thank you very much, Daniel, for your very kind introduction. First of all, I would like to thank the organizing committee, particularly Marisa, for your very kind invitation, for giving me this very excellent opportunity to join this very exciting event. Actually, this is the first time for me to join the National Organic Conference in the United States. So this slide, yes. I would like also to take this great opportunity to say, to express my sincere congratulations to Professor Larry Overman. You're receiving this prestige award. So Larry is a very old friend of our institute. I shot this picture taken 7 years ago. At that time, Larry gave a one-year memorial lecture at SLC. Thank you so much for your great chemistry and very nice lecture at SLC. The title today I'm going to talk about is asymmetric catalysis. Actually, when I came back to China from Japan, joined the SLC, I started my independent career in the area of asymmetric catalysis in 1999. At that time, actually, that is a very exciting research area for me, because before that, when I did a postdoc, I studied photochemistry when I was in Japan. And when I do a PhD, I studied physical organic chemistry. So the asymmetric catalysis was a very exciting research area for me. At that time, the asymmetric catalysis in 2001 awarded the Nobel Prize for three outstanding scientists. And there are so many breakthroughs have been done by scientists. But if you take a look at the real application of chiral technology, particularly asymmetric catalysis technology, there were only several tens examples. So what is a real, let's say, challenging issue remain in this area? So at that time, we considered probably the selectivity is one of the challenging issues for the asymmetric catalysis, because there is no any catalyst or chiral ligand which are universal for any type of reactions or any type of substrate. So we need a catalyst diversity to match different type of reactions or a different type of substrate. The most challenging issue is efficiency. If you take a look at the literature, many report you have to use 1 to 10% more of the catalyst for getting a high selectivity or a high yield of the product. So the efficiency is a key issue for the practical application of the chiral technology. So we need to significantly enhance the catalytic activity of the catalysis to reduce the catalyst loading by 2 or 3 order of the magnitude. And for the process chemistry, we need to find a good catalyst for the customer in a very short time. And other issues we have to consider. For example, if we cannot solve the problem of the efficiency, we have to think about recovery and the reuse of the catalyst, and the cost, energy solvent, safety, and other issues we have to think about when we utilize the chiral technology. And one of the approach we employed for the discovery of the highly efficient chiral catalyst is the combinatorial chemistry approach. By taking the high diversity and the high efficiency in the catalysis. Particularly for the chiral catalyst design, we focus on the use of a 2-component ligand. By taking the synergistic effect of the component ligand to make a ligand catalyst library, and then we can make a synthesis, parallel synthesis, and high throughput screening. So on the basis of such kind of approach, we have been successful in a variety of asymmetrical transformation, including heterodystrata reaction, reopening reaction, carbonyl yin reaction, and hydrogenation reactions. Here I just show one example. We developed on the basis of a combinatorial chemistry approach. So this is a very simple reaction, heterodystrata reaction, to give such kind of a heterocyclic product. Just a simple transformation of this product, you can get a beta, such kind of a lactam. This is a very important unit in such kind of building drug molecules. So here I show the background of the research in this heterodystrata reaction of dineshiftidine with aldehyde. So there are so many chiral acid that have been reported before our research. Particularly, here I should mention one of the breakthroughs made by Professor Michael Doyle. His audience here. Of course, in many cases, people can get over 99% yield and 99% enantiomeric excess of the product. But 1 to 20% more of the chiral catalyst you have to use. This is too much, actually. So one of the breakthroughs made by Professor Michael Doyle in 2001, they were able to utilize just 0.01 more % of the catalyst. That was amazing, actually. So for Lewis acid catalyzed such kind of a reaction. So small amount of the catalyst in this case. So with the inspiration, this breakthrough, we hope we can do something better in the future. So we utilize titanium. I like titanium metal actually. Titanium with a dioligand, we make a library on the basis of a2-component ligand strategy. Here is a ligand we employed for the creation of the chiral catalyst, a library, just 2 to 1, 2 ligand, 1 metal. You got over 100 catalysts. Here we set up 1 more % at the beginning, and then finally we are able to do the catalysis with just 0.1 to 0.005 more % of a titanium catalyst with this ligand, 2 ligand, 1 titanium, or a heterocombination combination of these 2 ligands with the titanium. We can do the reaction under solvent-free conditions at room temperature. The yield, giving the product with very high yield and very high in-and-chill selectivity. So this is some record actually at that time for this specific reaction. 2 years later, Professor Hashimoto at Hokkaido University, they were able to get such 0.002 more % of the rhodium catalyst loading for this reaction, giving the product high yield and high in-and-chill selectivity. So on the basis of a similar concept, we can do the carbonyl-yin reaction with the titanium catalyst of these 2 ligands at 0.1 to 0.01 more % of the catalyst, giving the product in high yield and very high in-and-chill selectivity. This is the most substrate we employed for the reaction, giving the product with a cyclic moiety here. And this still we utilize a very small amount of the catalyst. The product could be easily transformed to the such kind of a cyclic lactam, and one of the product could be used as a key intermediate of this drug. Actually, previously they have to use 5 more % of catalyst. Now, just 0.05 more % of the catalyst is enough for getting a high yield with a comparable in-and-chill selectivity in the product. So for such kind of a discovery of a highly efficient catalyst is some kind of a serendipity. We employ combinatorial chemistry approach, and we find a good catalyst by serendipity. So next example I want to show is how can we base, on the basis of a mechanistic understanding, to address the efficiency of the catalysis. This is a very simple reaction. The nucleophilic ring opening reaction of epoxide, giving such kind of amino alcohol with a 4 carbon atom. This is a key intermediate for the synthesis of this chiral anti-HIV drug, this part. And this reaction actually was reported many years ago, 1999, by Inaba in Japan. But they utilize 1 biennial, 1 titanium. So when we studied the kinetics of this reaction, we found that 2 biennial, 1 titanium is much better than 1-to-1 ratio, showing some kind of a ligand acceleration effect. And we also found that the addition of some amount of the water in the catalytic system is good, very good for the reaction. We found an accelerating effect of the water in the catalytic system, and we also observed a very strong, let's say, positive non-linear effect in the catalysis, showing that in the catalytic system, there were several species of titanium ligand species in the catalytic system. So we utilize NMR spectrum to follow the reaction of a biennial with titanium isopropoxide. When we mix two components together, immediately we observe the disappearance of the hydroxy group and the isopropoxide here. So showing that the reaction is very fast. And in the solution of biennial titanium isopropoxide and benzylamine, we observed a very strong peak of this species in the mass spectrometer of the solution. And showing that probably 2 biennial, 1 titanium, and 1 benzylamine are present in this species. So we utilize N15 labeled benzylamine to follow this species. We observed this peak change to 725, showing that the presence of the benzylamine in this species. And we utilize deuterated biennial and to follow this spectrum, we observed the 732 peak, showing that the presence of 2 biennial, 1 titanium, 1 benzylamine species. This is a base peak in the catalytic system, and after addition of the epoxide, we immediately observed the decrease of this intensity in the system, showing that the involvement of this species in the catalytic process. And we also studied the kinetics of this reaction, of course, but I didn't show the detail. And on the basis of this study, we proposed the mechanism involving 2 biennial, 1 titanium, probably it's an active species, and the epoxide according to with the titanium, you got activation of this epoxide, nucleophilic attack from here in the water act as a proton shuttle in the catalysis. So the 2 biennial, 1 titanium is an active species being involved in the catalysis, giving us a new opportunity by using ligand diversity to further improve the catalytic activity and the enantiomer selectivity on the basis of combinatorial chemistry approach. So finally, we optimize these 2 ligands, hetero combination of these 2 ligands with titanium isopropoxide to 0.5 more %. Catalyst loading, the room temperature intolerant, we can do this reaction in almost a quantitative yield and with a 99% enantiomeric excess in the 10th gram scale in the lab. This is very important. 99% EE of the product is very important, particularly for the liquid product in the synthesis of the chiral drug. So this example shows that some kind of a cooperation effect of the ligand between 2 ligands, the synergistic effect of the ligand. Next example I want to show here is a cyanation reaction of the aldehyde. This is, of course, a very simple reaction, but here I want to emphasize the cooperation effect of the 2 silane titanium unit in the catalysis. This is the product of this reaction are very useful in the pharmaceutical production and the agrochemical production, as well as many synthesis of many amino acid derivatives. There are over 100 catalytic systems have been developed for this specific reaction. Very early stage of this reaction, Oguni and Professor Jiang in China, and many other professors like Feng, Professor Corey, Professor Shibasaki. These catalysts are very good actually for the control of the enantiomer selectivity. but still they have to use 10% more or even more catalyst loading for getting a high selectivity. So two breakthroughs in the development of this reaction I have to mention here. One is reported by Biocon in 1999. They found that such kind of silane titanium dimeric species is active. It's a real active species in the catalysis. They are able to do the reaction with 0.1% more of the catalyst loading, give the product in about 90% in enantiomeric excess at minus 40 degrees. Another breakthrough was done by Professor Oguma at Hokkaido University using Nori-type ruthenium catalyst. They can further reduce the catalyst loading to 0.01% more at minus 78 degrees to give the product in 98% in enantiomeric excess. So we are particularly interested in this type of titanium, silane titanium complex. The mechanistic study showing that in solution, such kind of a dimeric complex exists equilibrium with the monomeric species, and the dimeric species is an active species for the catalysis, and this is not active for the catalysis. So such kind of equilibrium dissociation of the dimeric species will result in the activation of the catalysis. So we thought about if we put a linker between these two silane titanium units, probably we can prevent the dissociation of such kind of dimeric titanium, dinucleic titanium complex, and we get an activation of the catalysis, and such kind of a linker probably also might change the di-astute selectivity or enantiomer selectivity in the catalysis. So, of course, Professor Eric Jacobson also emphasized such kind of intramolecular carburetive effect in the kinetic resolution of the epoxide. So we designed a variety of the dimeric bridged silane ligand like this, like a linear, bridged linear. And after screening, we utilize 0.05% more of the catalyst loading. This ligand turns out to be best. So just, let's say, a few minutes, 5 minutes, you can get a quantitative conversion of the substrate and almost a quantitative yield of the product with a significantly enhanced enantiomer selectivity, 96%. And further reduce the catalyst loading allowed to get about, let's say, 200,000 turnover number in the catalysis, 0.0005% more of the catalyst. This is an extremely low loading in the Lewis acid catalyzed reaction. And here's a substrate scoop. I just skipped some. The red color substrate giving the product useful for the pharmaceutical, for the agrochemical industry, I show here. And we studied the kinetics. So it's interesting to find that the reaction is zero order to both substrate and the first order to the catalyst. The apparent activation energy is pretty low, and we didn't observe any nonlinear factor in the catalyst, showing that the two silane titanium units, the entirety of these catalysts being involved in the catalyst, single molecule. And we tried a lot of effort to get a single crystal of the titanium catalyst, but finally we failed. Alternatively, we got a cobalt complex of this silane ligand, this bridged ligand, showing that the silane metal species take a face-to-face orientation in this molecule. You can see here, and providing a very good opportunity for undergoing collaborative action in the catalysis. The involvement of the both substrate, cyanide and benzaldehyde, are not very difficult, and the intramolecular nucleophilic attack of the cyanide to the carbonyl group here is probably rate determining step here. And with this understanding, we are able to utilize the potassium or sodium cyanide as a source of the cyanide group, and we can do this asymmetric cyanation with this very cheap, very relatively safety. Because the TMS thing is liquid and volatile, it's very toxic. This is a relatively safe, it's easy manipulation. And giving the product with a comparable in-and-two selectivity and still high activity. So here I skip the optimization of the reaction condition. Finally, this table shows the substrate scope. We can utilize 0.005% more of the catalyst to do the cyanation in the presence of this anhydride. We got the high yield of the product and the comparable in-and-two selectivity in this specific reaction. And of course, now we employed such kind of process for the industry. Industry can make a tons scale of the product very recently. The next example I want to show here is a collaborative effect of the two chelating unit in one ligand molecule. This is a SKP ligand was reported, developed very recently in our group. And the story starting from the development of such kind of a spin-fox ligand. So we got an inspiration from the Albert Cheng University, Hong Kong Polytechnic University, and Professor Fars reported such kind of a Fox ligand, PN ligand. And Professor Zhou Qili in Nankai University, China, reported such kind of spiral-based phosphine oxazoline ligand. So we are particularly like this spiral backbone. But the difficulty associated with this molecule is there are three chiral centers here. It's a preparation. It's a pretty tedious actually. The separation of the diastereomer very challenging. So we removed the chiral center here to put a double bond, and they allowed the preparation of this ligand relatively easy. And with this spin-fox iridium complex, we can do the hydrogenation of imine. Hydrogenation of the imine is pretty challenging because of the product amines sometimes cause the poisoning of the catalyst. And this catalyst is particularly useful for the N-alkyl substrate and the heterocyclic substrate I show here. And for the hydrogenation of this substrate, the methyl imine, we can get this chiral drug in one step with over 99% in-and-two molecular excess by using this catalyst. Of course, this catalyst can be also utilized for the hydrogenation of such kind of alpha-beta unsaturated carbonyl compound and alpha-beta unsaturated carboxylic acid, and also for the hydrogenation of the alpha-beta unsaturated such kind of unreliable amide. So we thought about how about the hydrogenation of this molecule? Having double bond here, and after hydrogenation, you made the chiral center at the backbone of this molecule, and remove the methoxy group here, you got a cyclization probably. Of course, we can get a hydrogenation of this substrate in very high enantiomer selectivity. You got over 99% enantiomeric excess of this molecule. But after remove of the methyl group here with boron bromide, we got a racemization of such kind of spiral ketal. This is a big challenge actually. So we thought about if we can use a substrate having hydroxy group, probably we have opportunity to get an enantiomer form of such kind of spiral ketal. So why we do this chemistry? Because the synthesis of such kind of a spiral ketal with a catalytic asymmetric approach, it's a pretty big challenge actually. Even though there are many such kind of spiral ketal moiety units in the natural product. And also, such kind of spiral ketal skeleton are very useful framework in the design of the chiral ligand. This ligand SPAM-FOS was developed by Professor Van Leeuwen, and we developed this SPAM box based on oxazo ligand. And its zinc or copper complex are pretty useful for asymmetric catalysis, for hydroxylation, chlorination. But the synthesis takes a long time. For example, to build this skeleton, we need 1 week reflecting in acetone. And we got this molecule. It takes us 3 steps to upload this amide and the separation of the diastereomer and the ring closing to give this. It takes 1 month for the preparation of the several hundred milligram. So, so we tried some catalytic asymmetric approach. By using our SPAM-FOS iridium complex, we are able to get such kind of a spiral ketal in very high yield and high diastereomeric selectivity and very high enantiomer selectivity. Of course, iridium FOS complex are also workable for this reaction, giving the product with a 99% enantiomeric excess. But the activity is not so high as this spin FOS iridium complex. With this catalytic system in hand, we are able to make such kind of a spiral ketal molecule very conveniently. Particularly, we are very much interested in the bromo substituted molecule with this type of skeleton. And here I showed more structure of the substrate. And now we are able to make such kind of spiral ketal based on the asymmetric hydrogenation using this SPAM-FOS iridium complex in one part, the hydrogenation and the spiral ketalization in one part. You get a spiral ketal, aromatic spiral ketal molecule very easily. Almost at the same time, Professor Benjamin List reported the chiral bronze-acid catalyzed spiral ketalization of this type of aliphatic spiral ketal molecule. With this molecule in hand, we are able to further transform this molecule to diphosphine ligand. So we call it a spiral ketal-based phosphine ligand, SKP ligand. And this is quite easy, just substitution of the bromide with the lithium. You got a dilithium species and the nucleophilic substitution. You got a moderate to high yield of this diphosphine ligand. With this ligand in hand, we thought about what is the application of such kind of ligand. So the palladium catalyzed symmetric allylic substitution is a very useful transformation activity since pioneering work by Professor Chiji and Troster. But the control of the reduced selectivity at the same time in-and-two selectivity are a big challenge. Although some report by Professor Hayashi, first Trost, particularly for the allylic combination of such kind of MPH adduct substrate. So we usually got a linear product because he is steric, less hindered. So this is a big challenge. For example, if we want to develop the asymmetric version, we tried a binap. We got a linear as a major. We utilize spiral bisphosphine ligand. We got a linear as a major. And we utilize Trost ligand. We got a linear as a major. So we also tried the Spanforce. Giving the product, this branched product, it's a major isomer, but the in-and-two selectivity was only moderate. So we are happy to see when we tried our SKP ligand turns out to be best, giving the product, the branched product in very high ratio and a high yield with a 96% in-and-two selectivity. This is a pretty happy at that time. And of course, the product is very useful, and just a simple transformation of this beta amino acid ester, we can get a beta lactam. You know, beta lactam is a very common unit in the medicinal chemistry. So here I shoot the slide, shoot the structure of the molecule, substrate scope. You can get many type of such kind of beta lactam. And all of these substrate are giving the product with a high in-and-two selectivity and a good yield of the product. And more substrate here. And the such kind of beta lactam having such this double bond here, we can do hydrogenation, we can do cyclopropionation, dihydroxylation, and 3+2 cycloadation and metathesis. So providing a very good molecule platform for the transformation of these beta lactam to the biologically interesting molecule. Actually, we screen, we ask some friend to screen this type of a molecule, and we found one of them showing a pretty nice biological activity in the anti-cancer activity with 20 nanomole IC50 value. I'm not a medicinal chemist, but very recently they are able to get a adduct of this small molecule with a microtubulin structure, showing that this molecule is very interesting in the protein, inside the protein. And the product, this product can be further transformed to the this key intermediate for the production of this isotimib. And just one step, microaddition, you got this molecule on the basic condition. Again, basic condition, you got this cyclized beta lactam in high yield, 70% yield. And just a two-step transformation, you got this billion drug, billion-dollar drug. And we published this work in angiovenation. Of course, in terms of the development of the synthetic methodology, we can stop here. We got a new catalyst, new pattern of the reaction, and we found some application. But when we studied the kinetics of this reaction, we utilize IR reactor to follow the reaction process. So we found that when we set up the IR reactors, the study material disappear. Just a few minutes. When you utilize 1% more of the catalyst, you got a complete conversion of the substrate, giving the product in 93% EE. And the reaction is so fast. And we utilize 0.1% more of catalyst loading. In 1 hour, you got a complete conversion of the substrate. And we can do the reaction with the 0.01% more of the catalyst loading, and giving the product in comparable yield and comparable in-and-chill selectivity, showing that this is a very special case in the asymmetric allelic combination. Because usually, if you take a look at literature, usually people utilize 1 to 5% more of the catalyst. This is a very special case. So we got a single crystal structure of this ligand, showing that the two phosphine atom takes a 6 angstrom distance, quite a long way, you know. So it's much longer than sun force or span force. So we saw probably this base phosphine ligand only act as a monodentate ligand, not base phosphine ligand. But when we block one phosphine atom here with a by oxidation reaction, so when we utilize this ligand for the catalysis, we got a dramatically decrease of the reduced selectivity and the in-and-chill selectivity in the catalysis, showing that both phosphine ligand works in the catalysis. And we try to isolate the palladium complex of this phosphine ligand. So we are successful to get this spin SKP palladium dichloride ligand. It's a transchelating pattern. The student was very happy about that. But when he tried this complex as a catalyst for the reaction, only got a very moderate activity and in-and-chill selectivity, showing that this is not real active species in the catalysis. Even it's not the catalyst precursor in the catalysis. Then we try to get an allele palladium complex with this ligand. This is such kind of expected allele palladium complex was not isolated. Instead, we isolated such kind of palladium complex with allele double bond here, shift to here, coordinate to palladium, and the formation of a CP bond, forming such kind of phosphonium species, cation here. So when we started the preparation of this complex with the allele phosphonium sort with the palladium 0, we got the same complex. So with such kind of complex in hand, we tried the catalytic activity and the in-and-chill selectivity in the reaction. We got a comparable in-and-chill selectivity in the catalysis, but the activity of this species is much lower than the in situ prepared the catalyst, showing that this is probably catalyst precursor, but it's not real catalytic active species involved in the catalysis. So we tried to use the substrate to get the palladium complex with this ligand. So, but we failed to get a single crystal. We first prepared the phosphonium salt like this with the substrate, and we utilized this phosphonium species as to do the stoichiometric reaction with the palladium DBA species. Annually, we got a comparable yield and a comparable selectivity, in-and-chill selectivity in the catalysis. And But here, we can utilize mass spectrometer to observe these palladium species. But we don't know the structure of such kind of species. We only know, get the composition information. But finally, when we introduce such kind of a carboxylic ester group here, we are able to get these palladium species at a low temperature. We isolated this complex, and we utilize this complex for the catalysis. Except we got a 5 minutes incubation time. And then we observed the comparable activity with the in situ prepared complex. And this complex undergoes such kind of equilibrium in solution with the CP bond here and without the CP bond. Such kind of at a high temperature, we only observed this species. And we studied the Hamilton plot of this reaction, showing that for both substrate, electron donating group are favorable for the catalysis. This is an unusual case. And also, the zero order to both substrate and the first order to the catalyst. The activation energy is pretty low, showing that the probably reductive elimination operates the CM bond formation in the last step. And we proposed such kind of mechanism in the catalysis, showing that the two phosphine atoms here, one phosphine atom at organocatalysis, nucleophilic catalysis, and another phosphine atom coordinated to palladium and undergo organometallic catalysis. The reductive elimination of the CM bond here is a rate determining step in the catalysis. This is obviously different from the traditional transition metal catalyzed asymmetrical allylic amination reaction. Now we understand the mechanism. We know the reason for why high activity in the catalysis. Now, how to make the ligand in larger scale? The student utilize such kind of fluoro substitute aldehyde, protection of hydroxy group directly, and condensation with the ketone, got this molecule in large scale. Very happy about that. 500 gram, got a 700 gram in the lab. And then hydrogenation, got a chiral center here. Without a separation of the catalyst, just introduction of the palladium, carbon, remove a benzyl group, you got a cyclization with a difluoro group here. Very good crystalline material with a 99%, over 99% enantiomeric excess. And the nucleophilic substitution of difluoro here, and you got a diphosphine. This is commercially available. Just simply mixing together reflects separation and concentration, crystallization. Got a white powder of this diphosphine ligand. Now this ligand commercially available in SRAM diethyl, and the new process for the production of this beta-lactam for the production of azacitidine licensed to the industry in Shanghai. And now this ligand are widely used for the asymmetrical catalysis. This was reported by Professor Nakao in Kyoto University. They can utilize for such kind of amino cyanation reaction with alkene. And my colleague, Professor Zhou Jian, they are able to utilize this SKB good dinuclear complex for the cyclopropanation. It's workable for any type of olefin, monosubstrate, disubstrate, cis and trans. This is wonderful. Let me summarize my talk. In the first part, I talk about the development of such kind of titanium complex on the basis of a ligand cooperation effect. And this is a catalyst cooperation effect, intramolecular. And in this case, I talk about the story from spin fox to SKP, and in the SKP ligand, two chelating unit, phosphine atom here, take a different action in the catalysis, organocatalysis and organometallic catalysis, providing a new activation model in the asymmetrical catalysis, giving the product in high activity. Finally, I would like to thank my co-workers. They highlighted the name, the student, the postdoc in my group are being involved in the research results today I'm talking about, and the foundation from NSFC, from Ministry of Science and Technology, and the Chinese Academy of Science, as well as the Shanghai local government and the Merck Research Laboratories. I highly appreciate it. And finally, I would like to thank you for your kind attention, my lecture. Thank you very much.
And obviously, thank you for dealing with our technical
It's my, thank you.
So are there questions from the audience?
Sure, you got hungry. It's the time for lunch.
I can just start off with a question. Going back to your asymmetric cyanation, are you able to do that with more than just aldehydes? Can you?
It's a very good question. So we tried the imine, we tried the ketone. It doesn't work. Only for aldehyde, no.
Does it not work because of the asymmetric induction or the
activity is very low. Yeah. That is a problem of the asymmetric catalysis in many systems. Actually, when you develop the good catalyst, but it doesn't work for the useful substrate sometimes. Yeah.
Any? Oh, they are hungry. Okay. Oh wait, we have one back here. Right, standing up.
Hi, my name is Matt Goldfeld. I'm from UNC Chapel Hill.
Yeah.
I'm wondering if you can make any modifications to the phosphine substituents in order to tune the Lewis basicity or the donating properties of your liquid.
Yeah, very good suggestion. We only, right now, we only have several aromatic substitute phosphine ligand. So we tried some alkyl substitute to phosphine moiety to increase the nucleophilicity of the moiety. So we are now doing that. Thank you.
It is hard to see. Okay. If there are no other questions, or if there are other questions, you can move